Tous de DDO, attention pour les décomptes finales. 10, 9, 8, 7.
It's morning lunch, almost 3:30, and we're gonna make our fueling go or no go call soon.
Okay, take it away, Rob. It's all yours.
Merry Christmas from the Guyana Space Center, where fueling of the vehicle is moments away, while Webb systems are being carefully monitored for the momentous launch of the largest, most powerful telescope ever sent away from our planet.
It is the product of a feat of human ingenuity.
14 countries all working together.
We want to look back and see some of the very first stars and galaxies that were born in the early universe.
What we call cosmic dawn. We have to accept the fact that we are in a risky business.
Everybody said if James Webb is unsuccessful, then NASA will never take on a big challenge again.
There's a little pond down here. Yes, there still is. Used to come fishing here occasionally. Well, I would like to tell you the entire story of the universe and a bit about how we learned about it and my personal part of this process and where we're going from here. And the title slide here says from the Big Bang and on, etc., to the discovery of alien life. And so we haven't exactly found it yet, but I think it's possible in the next few decades. And so I want to outline at the very end how we are hoping to find out about that. So there are many, many mysteries. I got interested in math and science when I was a little kid. Here is a picture of the place where I grew up. My dad was a scientist, but he studied dairy cows. I heard from him that people are made out of cells with chromosomes. I can remember I was about 6 years old and I'd heard about infinity. Well, that's pretty fascinating. So, okay, I want to know more about this. By 8 years old, I was reading Galileo and Darwin biographies and getting all the books about science I could get from the public library. I latched on pretty early. I knew when I got into the mission that it was going to be exciting. I said, this is the coolest thing that I've ever heard of. This is what I want to work on. And I do not care how hard it is or how long it's going to take. I just want to work on it and make it happen.
I love the feeling of awe, but then sharing that excitement with someone is then the next best feeling in the world.
It's super close, but it's not.
Oh, these two? One of the things growing up in the city that we didn't really ever see was the sky. I do remember sort of one of these like core childhood memories is going up to Canada on a family vacation and my parents ushering me outside one night to look at the Milky Way. And I didn't understand what it was. And I was like, there's milk up there? They're like, no, that's our solar system. And we're looking up at all the stars that you wouldn't otherwise see. And I really didn't comprehend because I had no exposure to that prior in my life. And here I am, years later, following the astonishing story of the James Webb Space Telescope.
Nature has this way of being even more creative than we are. So we have always been surprised by what we see in the sky.
This is a really tremendous adventure that we've been on.
The first Hubble Deep Field actually came out when I was in high school. I already knew I wanted to be an astronomer, but I remember being just captivated by these images that were coming back from Hubble. It blew my mind to see that first deep field image, and that was sort of a like, yep, this is what I want to do.
The earliest conception of Webb derived from the fact that Hubble took a deep field and didn't see newly formed galaxies after the birth of the universe.
It's sort of like we're missing that very first piece of the puzzle of how galaxies got their start.
Every time NASA builds a new telescope, it needs to be way more sensitive than anything we've ever built before. So every time you launch something, it was a new window on the universe. And so for Webb, we needed to build something that was 100 times more capable.
The main thing that Webb had to do to be successful was find these very first galaxies.
To look back in time to a part of space that we've never seen before and see the very first epoch of galaxies that were born after the Big Bang.
People think the Big Bang is a mystery because they think it's not what it is. The actual picture that we have as astronomers is the entire universe is expanding. The material is rushing apart from other material in a rather smooth, continuous way, while we see the galaxies rushing away from us. So what's going to make them rush apart? Well, something kicked them off that way. But since we imagine the universe is infinite, it has to be an infinitely large cause, whatever that is. So we just imagine running the movie backwards in our minds until it's different. So when you get farther enough back in time, the temperature, everything's mushed together. The galaxies are mushed together, the stars are mushed together, the atoms are mushed together, the atoms are torn apart into their constituent subatomic particles. So that's the movie you get if you run everything backwards. So then when you run out of imagine, you say, that's the Big Bang. So needless to say, astronomers have been imagining for a long time, what was this?
What would you call it if you could name it?
I just call it the expanding universe story. In Calvin and Hobbes, there was a different answer. Calvin called it the horrendous space kablooey. But that didn't catch.
I now ask you to step forward to receive your Nobel Prizes from the hands of His Majesty the King.
And it was March of 1996 when John Mather stopped in my office out here at Goddard and asked me if I'd like to work with him on a new telescope idea he was thinking about. And when John came by and said this, of course, this was before he had his Nobel Prize, but everybody knew, oh, if John asked you to work with him, you want to work with him. So I said, sure, that would be fun. I figured, well, I'd do that for a couple of years.
So, Dr. Smith, what is a Next Generation Space Telescope?
Well, the NGST, or Next Generation Space Telescope, is the logical successor to the Hubble Space Telescope, or HST. NGST is designed to see the first stars and galaxies that light up in the universe.
And, well, here we are, more than 25 years later. I'm still working on Webb.
Hello, Apollo 8. Administrator O'Keefe renamed the Next Generation Space Telescope to the James Webb Space Telescope in honor of James Webb, who was the second administrator of NASA. So why name it after this guy? Well, James Webb was largely responsible for the success of the Apollo program.
So you're going to have both science and technology appreciating your leadership in this field. I think this can be an asset, this program. I think in time, it's like a lot of things. It's sort of mid-journey, and therefore, what the hell are we making this trip for? That's right. But at the end of the thing, they may be glad we made it.
Columbia on the high gate, over.
Roger, the EVA is progressing beautifully.
The Webb telescope is kind of like my child, because I've been working on it since the first day that we started.
So when I started on Webb, my youngest son had just been born. Well, he's got a master's degree, he works at Johns Hopkins, and he's going to be 28. I had hair. I didn't need hearing aids or glasses. And yeah, it's a long time, but in hindsight, it's also a short time. We had this singular purpose for 25 years to make the James Webb Space Telescope a reality. People did think we were nuts at first because the technical challenges were so daunting and the number of things we had to advance or literally invent were numerous.
I remember we had a draftsman who was able to draw what we said on a whiteboard, and we said we needed a big telescope with a big baffle, a big umbrella to protect it from the heat of the sun. So he drew this on the whiteboard, and we all said, yeah, that looks pretty good. We need something like that, and it's going to have to fold up, and we started talking about how to fold it up, and that was just the beginning, and we knew we were onto something.
In the early parts of the mission, we talk to the scientists and we find out what's the scientific objectives of this mission. What do you want it to do, right? Then we put that into a language that engineers understand called requirements. How big does it have to be? What kind of sensitivity do you want? In other words, what's the dimmest thing you want to see?
The James Webb Observatory has 3 parts to it. The first part is the telescope and the science instruments. This has to be very, very cold.
It's designed to collect infrared light. So infrared is something that you cannot really see with your eyes. The Hubble telescope can see a little bit of it, but it's not cold. So the Hubble telescope glows and emits infrared light itself, so you cannot use it to do all of the things that astronomers have identified as their next top priority. This telescope is going to be in outer space. It's going to be cooled to a very low temperature of 45 degrees above absolute zero, so that it does not glow.
There's one instrument in there called the MIRI that wants to be about 7 degrees Kelvin. And to put that in perspective, dry ice, carbon dioxide dry ice, is at about minus 109 degrees Fahrenheit. The second part is the spacecraft bus. And the spacecraft bus operates at room temperature, up here at 70 degrees Fahrenheit, and it has the usual subsystems, the communication subsystem, the computer, the thrusters, the electrical power system. Then, between the two, is the third part, the sun shield. 5 thin layers about the size of a tennis court that separate the hot side from the cold side. 5 little layers that keep this thing in the shadows. And this umbrella, as I might call it, is no ordinary umbrella. On the hot side, 200,000 watts of solar radiation strikes it, and it can only allow 0.02 watts to get through. This umbrella is setting up an almost 600 degree Fahrenheit difference. And if it were suntan lotion, it would have an SPF of 10 million.
And it's going to have to fold up, and we started talking about how to fold it up. And it's got to be bigger than the Hubble telescope. And it's got to get way out there, and we can't get it there without a pretty big rocket. So what's the biggest one you can get? Well, it's not all that big. We're going to have to make a telescope that's much bigger than the Hubble and simultaneously much lighter. We ended up at half the mass and 7 times the collecting area.
All 13,670 pounds, all 6 metric tons of this has to be launched 1 million miles out in outer space. And it has to fit into a fairing that's only about 5 meters in diameter, when the size of this sun shield is 21 meters in diameter. So to do that, we have to fold it up like origami so that it fits into here.
Pretty soon we know our job is pretty hard. Okay, gonna have lots of inventions along the way. So we made up a list of 10 inventions that we had to have pretty quickly. And we said, okay, world, tell us how you could make these inventions.
You have to keep in mind a lot of the technologies for web were new technologies, right? So you have a plan on how you're going to do it. And when you are testing it, lots of times something doesn't work. You have a schedule, a certain amount of time, and a certain amount of money.
Basically, people, although they don't quite say so, they think, your telescope looks weird. So our telescope does look different from every other telescope you've ever seen. It doesn't look like Galileo's little tube with a lens at each end. Way different from anything that we've ever built for anywhere before.
We're building a perfectly great telescope on the ground. We're aligning on the ground. We're testing on the ground. It's going to work perfectly, right? It's going to be great. Then what do? We bust it up. We fold it up. We put it into a launch vehicle. Then once we get it on orbit and it deploys, now we got to realign it on orbit remotely.
50 of the most complex deployments ever attempted robotically.
The telescope looks weird, but that's a matter of perspective. To me, it looks beautiful.
So that's your mission if you choose to accept it.
Yes, we had 344 single-point failures, 295 of which were associated with deployment, almost all of which would have been mission-ending.
So with Webb, we should probably go back to 1990 with the launch of the Hubble Space Telescope. And liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
NASA launches the Hubble Space Telescope, the biggest space science mission ever.
Discovery Houston, performance is nominal.
And shortly thereafter, it's discovered that its vision is blurry.
The conclusion we've come to from that is that there's a significant spherical aberration appears to be present in the optics.
I was devastated because I'd worked my entire career on Hubble at that point.
Congress had hearings. Hubble's the butt of late night TV jokes. It becomes a major embarrassment and major black eye for the agency.
Although the surface of the mirror was perfectly smooth, the smoothest mirror ever made by humans on Earth, the trouble is it was too flat at the edges, about a millionth of an inch, which is less than the diameter of human hair. That was enough to cause the tremendously blurry images that we saw. My neighbors, who all used to be very, happy and congratulating me on working at Hubble, they'd come up to me when I'm pushing my son around in the stroller and say, "Boy, it must be tough working on a national disaster." We can characterize the problem, the spherical aberration problem, well enough that we can take advantage of an insurance policy that we haven't talked much about. And that is, we started a long time ago to plan a maintenance program. That is, every 3 years we plan to go up with the space shuttle, change out instruments, change out things that broke.
I come to NASA in 1991 as part of the team to help fix the Hubble Space Telescope. I end up leading a team that's developing corrective optics for the telescope. Astronauts install the corrective optics and a new updated camera.
It's completely awesome out here. A lot of work, but well worth it.
And after 5 EVAs, spacewalks, the astronauts came home, and about 2 weeks later, we took off the bandages from our eyes, and suddenly Hubble was fixed. It was totally fixed.
The most significant contact lens in American history. Over here is the picture taken after the servicing mission.
And it works beautifully, in fact, better than original requirements. And it's still working today as one of the most powerful instruments of science ever created.
This is one of the things about building JWST. We didn't have that luxury at L2, where we couldn't service it. We knew that.
The L2 point is chosen for the Webb telescope because it's the first place where you can go, where the Earth and the Sun are always in the same direction, and so you can put up your one-sided umbrella and protect your telescope. Which you want to do either to keep the telescope cold, like the Webb. If you send it another few feet farther out, it'll eventually escape and go away from Earth. If you let it, say, a few feet closer in, it'll fall back towards Earth and have some kind of interesting chaotic orbit. Anyway, you wouldn't like that. So it's the boundary between Earth orbit and solar orbit. And that's a good place.
We knew that this mission was going to require a number of test facility, production facilities, and test facilities that didn't exist in the world.
Right from the very beginning, we were told to please develop an international partnership to construct the Webb telescope.
Webb is a global effort. NASA, ESA, CSA, and contractors all working together. It was 14 countries and more than 29 states all contributing to Webb.
I always called it the giggle factor a little bit. Like, can we really do this?
This new telescope has, I think, about 64 megapixels.
It's not like we could build and test things in those early days. So we were living in virtual land as far as computer simulations, computer modeling. We had picked our architecture in late 2002, and obviously that's when things got really, really busy with trying to make this architecture feasible. Because I would say even at that point we were not quite sure it would all work at that time. It just seemed so far out.
Let's keep making progress on the telescope, because the more we get done, the better the chance that this thing will keep going as a program.
I think of the technologies, the ones that I remember were most challenging were developing the material for the primary mirrors. We had a big effort to determine what that material would be.
And it was a kind of exotic choice. We chose a material called beryllium, which is element number 4 in the periodic table. It's extremely stiff, extremely light.
It was the cryogenic properties of beryllium that really won out. It's how stable it was at cold temperatures and its thermal conductivity, how thermally stable things were.
We mine the ore, we have to drill through and blast the rhyolite and remove that to get the volcanic ash layer where the beryllium is.
10,000 years ago, this was the bottom of Lake Bonneville, and millions of years ago, it was an ancient ocean.
So then it's pressed into this 550-pound block that's then machined out till it's about 50 pounds. Once that block is machined out to about 50 pounds, the backside is honeycombed. It's really cool looking. The front side gets polished. We're attaching motors to the back so the mirrors can actually move and flex up in space so they can align. Then what we do is we actually subtract off gravity. So we're building this in a place that has gravity. This telescope operates in space that has no gravity. The temperature change that happens between Earth and space actually deforms the mirror significantly.
You literally polish, the wrong surface into a mirror so that when they cool down and they change their shape as they cool, it's the right surface.
And so we actually make the mirror less good on Earth so it can be more perfect in space.
We would then send them to Huntsville, Alabama, where we would test them at Marshall, and we would cool them down to these very cold temperatures and measure with a special test device how they change as they cool down.
Let's talk a little bit about those 18 iconic gold mirrors that are actually on this telescope. Amber, can you tell us about the science behind those mirrors?
So the reason the mirrors are gold in the first place is because gold is a good reflector of infrared light. So we've already talked about how Webb will view the universe in the infrared part of the spectrum. And that means it will see light that's just a little bit more red than visible light, than what your eyes can see. And so it turns out that gold reflects that type of light really well. So that's sort of the science behind why the mirror is gold.
So these are things that people don't realize it takes to get a telescope like the Webb telescope built.
But every week that went by, we started getting questions of like, why is this taking so long? And is this going to go on for, and there was a lot of pressure.
Okay, the Committee on Science, Space, and Technology have come to order. The James Webb Space Telescope has been identified by the astrophysics community as its top priority.
There were voices out there. There was talk of, let's cancel this thing. There was always a concern of mine personally from long before. We could end up like the superconducting super collider, right? Don't want Webb to end up like that. A really large science project ended up being too much and too long, and people lost the stomach to see it through.
Thank you for the question.
Congress got really worried about our Webb telescope and said, isn't that kind of crazy not to be able to service it? And the answer is, yeah, that's the only choice we had.
The James Webb Space Telescope is another case study of NASA's mismanagement.
I know this is
How can we justify
I hope that we don't lose sight of why the United States is undertaking this complex mission in the first place.
If James Webb is fully funded, NASA will be on track to launch the largest and most powerful space observatory ever built.
The average person would be like, I couldn't, bear the pressure and anxiety and stuff. And what's the secret?
Yeah, how do you handle the pressure of something like this is an amazing question. I will say the bonds that we built through failure and then through success, of course, it was a family. We argued.
The position is the mom, mission operations manager, and it was the job is kind of sometimes like being the mom for everybody. So everybody in here, I almost, you get to the point where you're almost personally putting them into the positions, and you're kind of helping them grow into what's going to happen. You try to prepare them, because I would tell people that it was a very stressful job as we got closer. And you had to kind of work with people to help them deal with the stress and stuff like that. So it was, you tend to be a mom, be a good friend.
We all knew the risks. We all knew this wasn't a sure thing. None of us left. That's what I'm proud of.
first and foremost, we were ourselves, and we brought our strengths and we brought our colorful parts of ourselves. The way we survived, ultimately though, if I could attribute to one thing is, the more the naysayers came at us, the more we as a team bound together. If the naysayers thought they were going to cancel this program by what they did, they only made us stronger.
In the early times, up until now practically, the budget was not what the project actually required. The budget was what people could get for us. And so it didn't change until Senator Mikulski wrote a letter and said, "We're tired of hearing from you guys. When are you going to tell us the real number?" She didn't say it in those words exactly, but please stop embarrassing us. So what's the real number?
2, 1. Senator?
Good morning, Goddard. How are we today? I am so happy to be here with you in the new year.
What led to us persisting were people like Senator Mikulski, who was a huge advocate for Webb and for NASA Goddard and for science in general. The science community was largely solidly behind Webb because they knew the potential this thing had and how important it was.
When we go into space, we don't go to conquer, we go to discover new things about the universe.
We finish assembling it and ship it off to NASA.
We really don't know any much about it. We know that it was 18 pieces. We have pictures of what it was like. Yeah. And get back into it. And that's about it. Everything else is sort of secretive. We just take it from point A to point B. Each mirror is worth about 20. And we have 3 in the trailer, so that's $60 million. And if we drove the truck thinking constantly that there was $60 million in the trailer, we'd probably just drive ourselves crazy and nervous wreck up here. We just have to treat it like everything else and drive it and do our job. Bye, guys. That new space mirror thing that we're carrying in the trailer, it's going to be a little over 1 million miles away. And we've driven 1.3 million on the last truck. So it's going to be really far, I can tell you. You know, because 1 million miles is a long time behind the wheel of a truck. So I can tell you 1 million miles far away is a long distance. It's real. I've seen it. I've seen crates that the mirrors go in. I've seen the drawing of what the mirrors are going to look like once it's put together. You've got 18 of them all hooked together. So then you have to imagine that they're folding each one of these up and then they're opening all up at the same time. It's just like a flower. It's going to be beautiful.
I have a little trouble sleeping knowing that these mirrors are on a truck crossing the country. These are the final 3 mirror segments for the James Webb Space Telescope. So yeah, an incredible milestone here today. Exciting.
We're getting up early for it.
Absolutely, worth getting up early and standing here in the cold, sure. These mirrors will literally see light from the first galaxies that were born in the universe. So, exciting stuff. This is where we take all the VIPs that come through Goddard. So, you guys are definitely VIPs.
Oh my God.
So, yeah, this is the world's biggest clean room of its type. And if you look right up there, you'll see the familiar pods that have been on your truck over the last year.
They're gorgeous.
They are. They're beautiful. And so this big yellow structure here is where we're going to assemble the mirrors onto the back plane of the telescope. So it'll sit flat, and then that robotic arm right over there will take all the mirrors and place them down on the back plane. So yeah, we have to keep everything clean so that once it gets out to the clean part of space, it's, you know, it's already clean. Mm-hmm.
It really is clean.
Yeah, and I mean, you see the guys in the bunny suits down here, so they have to stay protected. And that whole wall over here is air filters
So I guess you can't smoke in there.
Can't eat
Definitely
chicken
not.
wings in there
No,
either.
no,
Bummer.
no chicken wings
No
allowed in
beer?
the clean room.
No TVs?
Everything's so clean now.
They're busy though.
This is
Yeah.
just remarkable.
Yeah.
So when
What's
we
it
watch
like,
this thing take off and we know that it's in space,
Oh, that's fine.
we were
Yeah.
there.
Yeah.
We saw it.
It's a very tense scene in here when these two guys from L3 Harris were working over the primary mirror to take those covers off. They'd been practicing for a couple weeks before this, but this is a very delicate procedure. Any misstep could damage the primary mirror. Even if they have a drop of sweat that falls off onto the mirror, that could set the mission back, 6 months or a year or so, because they're working to clean that.
At one point, they told us they needed silence. So a lot of us, including myself, just took a step back.
And this is something we really do not like to do on Webb or on any telescope, is be above the optics, having humans above the optics. So, and it's something that I've done quite a few times on Webb. The technician is on a diving board, which is attached to a forklift, is basically a harness platform attached to a forklift out over the primary mirror. And then physically removing a hard cover from each mirror segment. The mirror segments are within millimeters of each other, and so it's very difficult to remove something without scratching or damaging the optical surface. So it was a very delicate operation, and really just showed how careful we were going to need to be.
It was wonderful. It was wonderful to see the instruments coming to the clean room, being aligned. I think people know once we are on these chambers, it's a big effort to keep them cold. So we work 24 hours a day, 7 days a week for 3 months.
I mean, I knew that Webb was a really big deal because they were just putting the mirrors together when I got here. I mean, you can't not appreciate how it looks because it's huge and it's gold and it's beautiful and it's just so different from anything else. But one of my important life memories really was the first time going in the clean room. And there's something really special about putting on a bunny suit, especially for going in for work. I never lost my appreciation of putting on a bunny suit, opening those doors, and seeing a space telescope in a room. Generally for the job, we are documenting what the engineers and the technicians are doing. And it's not typical for producers to come in overnight to shoot sort of glamour shots of something. So we got permission from the project to come in and give Webb a really special treatment with these shots. We got a lighting crew, cleaned a lot of gear into the clean room, and these really became some of the iconic shots of the telescope. I do think we got more embedded into a team than a lot of other media groups have. But yeah, you totally feel a part of the team when you are dressed like the rest of the team. And then you get to know your team from this lens. There's some people that I only ever encountered in the clean room and was shocked to see what they actually looked like outside of the clean room.
So Paul, go ahead and take us on a tour of the facility. And I might note, this is the same facility that for many years was used to develop the surfacing hardware for the Hubble Space Telescope. So it's moving on to its next generation. Paul, it's all yours.
So there are 4 instruments and the science instrument module itself.
Webb has 4 state-of-the-art science instruments and a guider. The instruments consist of a collection of high-resolution cameras that give you the pretty pictures, and spectrographs. And the spectrographs are the real scientific muscle behind James Webb. They're the ones that can tease out the signals that tells you the physics and the chemistry of the objects they're looking at.
Behind every image and spectra that we are seeing from Webb, our instrument has to work. So NASA asked the Canadian agency to contribute the fine guidance sensor. That instrument is one that looks for a particular star in the sky, what we call a guide star. Once it finds it, it keeps that position. The intent is to keep the observatory as stable as possible. If you want to take a picture with your camera and your camera is moving, that picture is not going to be good. So we do the same on orbit with this instrument that I look after, and that's a complex operation. I'm an astrophysicist, but I work as a systems engineer on the James Webb Space Telescope, in particular looking after two of the instruments, one of the science instruments and the instrument that guides the telescope to let it take all these pictures that we're seeing.
The system would not guide without the guide. She was the systems person for the guider, and it was such a complex thing to do guiding. There are so many technical details. She had her arms around all of it.
I don't know how we could have gotten through all of the complicated way to verify that Webb could point and track properly. That was a complicated thing to prove to ourselves that that was all going to work, and Begonia was key to that.
And what was great about her was she had this personality which was so positive.
Which is where you have it.
All right.
So I grew up in Spain. I did my degree there. Then I did my PhD in astrophysics in the UK. And then I think for family reasons, we ended up moving to Canada. And in there, I moved to the private sector, but to the space industry. So I started actually in Canada as the technical lead for the two instruments that were the contribution to this telescope from Canada. And of course, all these things are super careful. You have each instrument is built to meet what they need to do on orbit. Each of them has been tested to show that it can survive the worst part, the launch with the vibration and the noise, the acoustics. We had 3 of these tests on the chamber here at Goddard. The first one had 2 of the instruments, the Canadian and one of the European ones.
Good morning. I'm Chris Calise, Director of the Goddard Space Flight Center. Welcome to the center. I'm standing in Building 29, and behind me is the clean room where we're building the James Webb Space Telescope. And as you can see behind me are the 18 mirrors that form the telescope. Now, so that you can start hearing about the telescope, I want to introduce John Mather.
Thank you, Chris. Well, welcome to our science party here today. I think it's a wonderful day to celebrate, and I want to tell you a little bit about what we're doing it for. Today, we're celebrating the fact that our telescope is finished, and we're about to prove that it works. So that's a pretty important milestone for today.
When you're launching in a rocket, it's what we call random vibe. It's just random shaking, right? We did what we called a signed vibe test, which is essentially vibrate the thing at a given frequency.
Where we literally will shake the full telescope to simulate the effects of launch.
And then change the frequency slowly and watch how your system behaves. It's a much more stressing test. But that means that you have the possibility of over-testing certain parts. Certain parts resonate at certain frequencies. And when they start resonating and you go 3, 4, 5, 6, 7 vibrations, you start building up energy.
You start with a little shake, and then you go up and you shake it a little harder, and you shake it a little harder. There was a loud popping sound, and the sensors measured something that was exceeding the levels that we said, if this happens, automatically shut down. So we had an automatic shutdown. And I still very much remember because it happened on a Saturday, and I was actually home during that particular test. And I get a call, there's going to be a telecom. We just had an automatic shutdown, and there was a loud popping sound. And the popping sound gets your attention because you're not supposed to have a popping sound when you test flight hardware. And I literally drove into Goddard. You know, I'm like listening to the telecom and driving. And we started discussing whether that popping sound could be potentially, you know, something broke. The telescope was actually covered in this like plastic material, and it's purged with dry gas, but you can see through the plastic material. So I literally climbed under the telescope with the phone in my ear, and I'm looking at it, and I said, you know, I don't see anything visibly broken, like nothing came off. And it was really difficult to figure out, but it turned out, we started running a separate test of some of the launch restraint mechanisms and the systems that keep it latched up. And we found out what the problem was, which was at a certain level, these things started to chatter. And that chatter sounded like the popping sound that we heard. We call that gapping. We convinced ourselves that we were going to be okay for launch.
There is so much at stake. I mean, I love the drama of it all, but you have to understand that people's careers are made from something like this. And Webb was a mission that was going to be spectacular, whether that was good or bad, if it failed or was successful. It was going to always make history.
Everybody's pushing to accomplish something that's been outlined as an idea. The inspiration of trying to discover something, to build something that's never been built before, to discover something that's never been known before. It keeps us going, and we are pleased and privileged in our position here at NASA to be able to carry out this on behalf of the country and the world.
This center of curvature testing was in the main Goddard clean room, the largest clean room at Goddard, and it's a fantastic facility, but even that is at the limit of what we needed for Webb.
The telescope's optical segment, the part with the mirrors and the science instruments, was built at NASA Goddard in Greenbelt, Maryland, then hacked and flown to the Johnson Space Center in Houston, Texas.
We needed a very large chamber to test Webb end-to-end optically. So we wound up using JSC Chamber A, which is the same vacuum chamber that was used to test the Apollo landers.
And it's been a long way, but we're here.
Chamber A was designed to test the Apollo Surface and Command Module, so it had a rotating floor and a top and side solar simulators. So they would simulate the orbit of traveling to the moon, where the passive thermal control system for the Apollo would rotate, kind of do what they call a barbecue roll, and practice its heating and cooling. And we did that with actual astronauts. It was before my time, so when I say we did that, I'm talking NASA, not me personally.
Didn't really get used very much. I believe there was a worry that that it might be mothballed or demoed, and they wanted to preserve it, and they made it a National Historic Landmark.
So Chamber A, with its 40-foot diameter door, is a pop culture icon. It's been in music videos like Aerosmith. It's been in Armageddon and Transformers 3.
Still working on the preps for Webb when we were trying to clean up the high bay for the movie Transformers 3. And they had to get permission from Webb to film that, so that as not to interfere with the schedule of the telescope. The Webb was it was the most complicated thing that they had done since Apollo.
The goal of the tests of the telescope in Chamber A really was to make sure everything was functioning properly at the very cold temperatures, and all the optical systems work properly at cold temperatures. It was the one time we could test the entire telescope at the very cold temperatures. The test was nominally a 3-month test where we would cool the telescope down. It took almost a month to cool the telescope to this minus 400 degree Fahrenheit temperature. And then a little over a month, we'd stay at these very cold temperatures. And it was the first time we were going to test the full primary mirror as a mirror, because we'd only tested individual mirrors at that point. So we had to see that the shapes of all of them matched. It was the first time we were going to test the telescope, sort of end to end. Most of the cooling that we do actually is done with a very large liquid nitrogen canister inside of the vacuum chamber. We run liquid nitrogen through it, and that cools us down to about 75 degrees above absolute zero. To get even colder, we'll have a liquid helium system inside of that, but most of the cooling capacity comes from the liquid nitrogen itself. The sequence of the test was it takes about 30 days to cool everything down. We had about 30 days planned for testing, and then about 30 days to warm everything up.
So when you are planning for one of these tests in a chamber, you always do the contingency procedures. If this goes wrong, what will I do? And I still remember our first meeting for Houston, where we go through all the things we can do if the chamber loses power, if this instrument doesn't work, whatever. And then they say, well, we also have to plan for a hurricane. And I remember being there saying, what? Are you kidding me?
We started hearing about a storm that was brewing, a tropical storm. And we all kind of gathered in a room. We started talking about contingency planning because we had thought a lot about potential for storms and hurricanes. And we did have a 5-day supply of liquid nitrogen in case there was ever a big storm. You know, we got ready. The storm got upgraded and upgraded and upgraded to Category 3 and Category 4.
So we were monitoring, and I remember finishing my shift, and the hurricane, it seemed that it was going to come. And we were like, well, what shall we do? And they said, we'll know, so don't worry, go home. I remember going for dinner with some colleagues. We went to the restaurant for dinner. And when we left, the water, you know, we were paddling on water. The water on the street was as high as the sidewalk. So that night, the hurricane hit.
And Saturday morning came, and you know, the sky cleared a little bit, and we said, okay, well, it looks like we made it through the worst of it. The storm had kind of hit us. And so, you know, we had all these air mattresses, and a couple people stayed there Friday night. But we actually started doing testing again. And, you know, Saturday afternoon, we got the very first measurement of the primary mirror. The very first time we saw the entire primary mirror was right after the hurricane hit the next day. But literally within an hour or two of getting those first measurements, some of us actually had gone out to dinner to kind of celebrate. We made it through it. And while we're there, we get an email from the meteorologist that it looks like the storm is kind of coming around in a spiral, and we're going to get a much, much bigger hit that Saturday night.
Feeling the full force of hurricane. We're not measuring in inches of rain here. We're measuring in feet of rain. One of the most powerful storms in the United States. 130-mile-an-hour winds and a treacherous storm surge. Rescue efforts are underway.
You know, I think we got 51 inches of rain that week, but over 42 inches of it was in one night. And it was insane. And it was so intense that literally water started coming through the roof. So we started having to cover equipment.
I mean, you are there and you see the water come in, and then you see them coming and setting everything up. So we were just dealing with the day-to-day, you know. It was incredible to see, but at the same time, you know, we were just working and trying to accommodate all of these.
And it turned out that the storm lingered for a full 5 days. We had a 5-day supply of liquid nitrogen, but it was coming up on 5 days. And there was a point at which we would have had to do what's called an emergency warm-up and warm things up even faster than planned in a way that we had never done before in any of the rehearsals.
Pieces would have broken. You just can't have things change temperature that quickly when those kind of materials and expect them to survive.
If we couldn't get some liquid nitrogen, but the problem was the supplier of the liquid nitrogen was underwater.
It was a state of emergency was declared, and so getting our shipments of liquid nitrogen was not the priority of the state, and we had to make it happen.
The center did a great job of using our center resources to grab liquid nitrogen from every other point on the center and redumping it into our tanks.
And the teams, many of them slept in the control room. Hurricane Harvey was one of those times where the team gave up everything for the protection of the telescope.
We were literally at the very final day. I remember, you know, coming in really early in the morning, and after several hours, we finally got the president of the division that sort of ran the liquid nitrogen, and they were able to find a driver and find a truck and make a couple trucks of supply, and finally they came that night, or the next morning I think we would have had done an emergency warm-up and crossed our fingers a little bit. But they came, and I remember because we had a video camera of the place where the trucks would pull up, and when we saw the trucks, the entire control room broke into applause.
I was one of the first people in the chamber after when we opened it up. It was actually on my birthday. And it was one of the most powerful experiences of my time working on Webb. The chamber is amazing with the door shut. It's all black. It's designed to be not reflective for light, and so we went in with flashlights to do this inspection, and it's similar to spelunking. It's like going into a cave that has a space telescope in it. It is absolutely the coolest thing. We need to